Let's go ahead and talk about addition, subtraction of rational numbers. Again, what are rational numbers? Fractions. In the overall scheme of things, the overall scheme, the basic rule we have to follow you need to have common denominators. That's the bottom line before we do anything with addition and subtraction. Now, do we need the same rule when it comes to multiplication division? No. You only need this when it comes to addition and subtraction. Remember, we've introduced already what fractions are. Now we're going to see how we can compare them. Again, always resort first to manipulatives. So what manipulative would you use doing this one? We have only two possibilities. We have either a number line, or we have the a circle or boxes. So let's look at the first one. All right, so first off, we have to represent what is 2/5. Well, we have 5 boxes because that's what the bottom number tells us. And we shade 2 of those boxes. Then the other one is 1/5. We have 5 boxes. We shade 1 of the boxes. So when we add them together, we're still going to have 5 boxes. But now our solution is we have 3 of them shaded. We represent with manipulatives the equation that we're trying to let them see. So since there's 2 of them here and 1 of them, we have a total of 3. So it's now since we have the same bottom number, we only have to worry about the top. So we add the top. And that's what we're doing here. So that's how we introduce that concept to them. How about number lines? How do we do number lines? Well, since we're doing 2/5 plus 1/5, we have to cut our box down into fifths. All right, number line, I mean, not box. What is 5 over 5? 1. So now this is where the number 1 would be. So we're going everywhere from 0 to 1. As we did with number lines, we start off doing 2/5. So we start at 0, move over 2/5. We're adding one more spot. So that means the answer is 3/5. Pretty straightforward. That's because what kind of fractions are these? What kind? Yes, these are proper fractions. A proper fraction is when the top number is less than the bottom number. What if we had this example? Let's use the two methods again. Remember, if you don't want to use bars, you can always use a circle. And it's the same thing. It's just that these are harder to draw. So 3/5 would look like this. And then 4/5 would look like this. When you add them together, you take these three, shade those in. Now you got to add these four. 1, 2. Uh-oh. We're out of space. So what do? We can't just add boxes. Why? How many boxes do we have to add? You have to always go in groups of 5. You have to go in groups of 5. So we have these three, 1, 2, 3. We have 1, 2, 3, 4. So what's the answer going to be? Isn't it 7/10? That's what this is what kids are going to say. You have 7 shaded. Now there's 10 boxes. How would you answer that if you're, well, you will be the teacher. How would you answer that? 5 5s. Yeah, but the kids are saying we have 10 boxes. So isn't our denominator 10? How would you answer that? Remember, you're talking with elementary school kids. Remember what little they know so far. And you have to answer it in a way that's not going to make them feel stupid, and but going to give them encouragement and say, "Oh, that's a good idea. Now I see what you're talking about." The question still stands is, how would you answer this? We know what the answer is. Yeah, I said it earlier. If we look at algebraically, but again, now you're using manipulatives. That's what the kids are going to see. That's what they feel. That's going to stick with them. You have to now convince them what the answer should be. How do you get 7/5 if there's 10 boxes? That got me confused. That got me confused. The denominator doesn't add. Why? Why doesn't the denominator add? I have, if it's a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 boxes. So the bottom number should be 10. But it's not 10. Why is that the case? You see now why division is such a difficult concept. That's why people don't like it. Because once we reach this, remember, we're talking about bars. How many bars have we got solid here? We have one whole bar. Well, what this one says is this one is 5/5. They're all shaded. Remember, I added another box. And how many of those are now taken care of? What is 5/5? So this one tells me we've completed one set of bars. We needed to borrow two more from another set. This simply means put the two numbers together. But how come this number is different than this number? They're not the same thing. Smart kids. And this is where you were derailed when you were in elementary school, is the way the teacher described it or answered it to you didn't sink in. It didn't make sense to you. Because if it makes sense, like addition or subtraction, are the kids having a problem with doing addition or subtraction? No. Even multiplication. But when it comes to this now, we have a little bigger problem. What you would do is you would ask them, this is a true answer. This is a true answer. And we're going to get to a point where we're going to discuss these and why are they the same. That's in today's lecture. But you ask the kids, okay, since we know we start off with a bar with 5, that's our original one. So what is this? How much of the bar is each one of these? 1/5. This bar is 1/5 of that one. Then this one would be 2/5. Then this one would be 3/5. Then this one would be 4/5. Then this would be 5/5. And remember, I'm adding another bar, so it's still over 5. Now I have 6/5. And now I have 7/5. Because each one of these boxes are the same size. They're each 1/5 of a number. I add 7 of them. Right. Oh, 7/5. It's 7/5. Because even though there's 10 boxes, how big are these sets? There's 5 there, and there's 5 there. We could only deal with 5 numbers. So that's how we get 7/5. We just count 1/5, 2/5, 3/5, 4/5, 5/5, 6/5, 7/5. If we kept on going, this would be 8/5. This would be 9/5. This would be 10/5. What's 10/5? This is the number 2. This is the number 1. When we go to our number line now, we have 1, 2, 3, 4. 1, 2, 3, 4. So 3 over 5 plus 4 over 5. I can use, that's 1 over 5, 2 over 5. This is 3 over 5. This is 4 over 5. This is 5 over 5, which is 1. This is 6 over 5. And this is 7 over 5. So the choice of manipulative will make it easier to explain the problem. Wasn't it much easier doing it this way? Because it's always a jump. You had 3 jumps, 1, 2, 3. This is 3 over 5. Now we have to go 4 more. 1, 2, 3, 4. We ended up at 7 over 5. This number line was much easier than these cubes because the cubes gave the kids a confusing aspect. Because remember, we always said our fractions are always part over total. They're going to count. We have 10 boxes now. You're lying to me, teacher. They're going to say, then how can these be true? Easy. Since we're dealing with only 5, isn't this 5 over 5? So there's 1. And we go 2 more behind it. We go 2 more after that. We haven't gotten to the conversion yet. Y'all remember the conversion rule? How we go from, what's this number called? This is a mixed number, and this is a improper fraction because the top is bigger than the bottom. And then that is where you introduce improper fraction because our boxes only have 5 spaces, but we went beyond that space. Because we went bigger than that, we now have an improper fraction. I'll ruin the surprise and I'll give you the formula. What this number means, this means 5 over 5, and we have 2 more over 5. So that equals 7 over 5. But that's not the formula. That's just what we just talked about. The formula is this. Take the form is this, A, B, C. This is the, A is the integer, B is the numerator, C is the denominator. Remember, it's a fraction, so the C has to stay on the bottom. The top number, since this is a whole number, a whole number is how many of these boxes did we cover? How many of these boxes did we cover? So we take 1 times 5. So it's A times C. That tells you how many boxes we covered, how many full boxes. This is the leftover ones. That's the smaller ones. Then we add those as a remainder. Oop, that's B. So there's your formula. The coefficient minus denominator plus the numerator. So 1 times 5 plus 2. 1 times 5 is 5, plus 2 is 7 over 5. And you see what we're always doing also. What am I reinforcing here with this example? The math part. Order of operation. The more you can instill into their brains the order of operations, the more they can ingrain it to them, the better it's going to be. Because even I teach college math. I start off every semester, even my calculus 3 courses or higher courses, I always go through the order of operation rules. You would be surprised how many people don't know them. The properties of math, the associative. Remember, we talked about already the associative property, the commutative property, the distributive property. A lot of people don't know those. Why? Because their teachers never taught them that. How many of y'all never really heard those or seen them before till this semester? Or you may have seen it, but do you remember it? That's this. And it's math people shy away from. Besides that, you have a big problem. Growing up, if you ask kids in elementary school, what's your favorite subject? What are they going to tell you? Math. Why? Because math is nothing but manipulatives and games and activities. 5th grade, that stops. Because or 4th and 5th grade, because now you have that state test, the STAR test. You have to worry about it. You don't get manipulatives in STAR test. It has to be pencil and paper only. So you've done away with the fun stuff. Now you're stuck with the boring paper and math stuff. And then when you ask kids in high school and college, what's your most feared or worst subject? Math. And to be honest with you, mathematics, college algebra, is the subject that makes most people not graduate college. People will wait. They'll take 4 years of courses and save their algebra course to the very last course to meet the state requirements to graduate. If they don't pass that, guess what? They don't graduate. And they'll take it over and over. They'll go to other college, other schools, online, different, to find an easy way out. I don't want you to be that way. I'm going to show you guys should be able to take college algebra after this course because you'll have a basis, a background for it, especially if you take it with me. The definition of addition of rational numbers with like denominators. Because we have 2 types. We have with like denominators or unlike denominators. Like denominators is pretty easy. If we have 2 fractions, 2 rational numbers, if A over B and C over B are rational numbers, then A over B plus C over B equals A plus C over B. You have to you have to prove this with your first examples. Did we prove this earlier? Yeah. 2 over 5 plus 1 over 5 equals 3 over 5. That's the same thing as 2 plus 1 over 5. So we have to get to them to understand what we just did. Then we show them the theorem. Now we're good to go. There's another. Okay, what if we had different denominators? What if, how do we teach them this? Would cross multiplication work here? No. Cross multiplication only works when you're solving rational equation or proportions, fraction equal a fraction. What you have to do here is you have to share the denominators. Since this one has a B, this one doesn't, I have to give them a B. This one has a D, this one doesn't, so I have to give them a D. Are they the same denominators? Why? This is BD, this is DB. So what proof tells me that's the same number? You have to use a property. Which property tells me what I can do with them? Because remember, you're talking to the kids. When you say they have to be the same denominator, BD is not the same thing as DB to them. You have to convince it to them. What's the property? That's the reason it's so important to start off with properties. What do I have to do to make them equal? What did I just do there? More than that. What did I do? Not, you can't just say flip. There's no property that says flip. Not distribute. I can't say rotate because you have to think of a property. One of the words we use when we talk about properties. Flip is not one of them. Rotate's not one of them. Who said it? Yes. We moved them. We simply moved them. And we can move them because this is B times D is the same thing. B times D is the same thing as D times B because of the commutative property. Of multiplication. Because they're multiplied, I can move them back and forth. Now they're the same number. Because they're the same number, I can add the tops. And that's the theorem of adding unlike denominators, rational numbers. That's the definition of addition of rational numbers with unlike denominators. If A over B and C over D are rational numbers, then A over B plus C over D can be written as A over D plus CB. What formulas, what names have you learned growing up. That helps you. Because think about what we did here. How did these get put together? I multiply these together. That's how I got that one. I multiply these two together. That's how I got that one. How do I get this one? I multiplied these two together. Because the sign is plus, so what I have here is the butterfly method. I introduced this to a bunch of graduate students. They said they wish they would have known this process growing up because they were forced to memorize this rule, but there was nothing to make them really apply anything. This is it. Butterfly. You have the wings, which means B times C. This one is A times D, and they're added all over BD. It's all done for you there. You do something like that, the kids are going to remember it. I can tell you right now, there's a class of 20 some odd graduate students that use this when they do their division and their teacher classes. All right, here's some examples. Well, does that process work if you have the same denominators? Does the butterfly rule still apply? Well, let's see. Let's check it out. So these two are A times B. There's a plus. This is B times C. So we have AB plus BC over B times B. Look at the top. Do they have anything in common? They have a B in common. We can factor that out. 1B can cancel. And that's what we have. So it does work. Again, you have to keep on applying the rules or the properties that we've always dealt with. Example 6. 2 over 15 plus 4 over 21. Put those together. These are big numbers, aren't they? So let's not multiply them together. So up here would be 2 times 21. This would be 4 times 15. So we have 2 times 21 plus 4 times 15. And on the bottom, we have 15 times 21. Why did I do that? Because before you divide, Here's a rule that I'm interjecting here. Before dividing, whenever you add, simplify first. Before you add them together, simplify. What is 21 made up of? This is made up of 7 times 3. We have 4. 15 is made up of 3 times 5, right? So 15 is made up of 3 times 5. 21 is 3 times 7. What is 4 made up of? It's made up of 2 times 2. Let's factor. What is in common on top? We have 2 terms. What's in common with both of those terms? This one doesn't have 3 times 5. What's the same number in this number and in this number? What do they have in common? They both have a 2 in common, and they both have a 3 in common, right? So the 2 and 3 they have in common. We can factor out a 2 and a 3. So what goes inside the parentheses is that 7, that 2 times 5. We're using the factoring, the distributivity rule. And on the bottom, we have 3 times 3 times 5 times 7. Can anything cancel? Now, this 3 and this 3 cancels. Can we cancel those 7s? And well, you'll get that and say, but no, there's a little bit more to it than that. Because there's a plus sign. That's why. The parentheses really mean don't do anything. It's because there's a plus sign up there. So once we finish that, what do we have left? On top, we have a 2, 7 plus 2 times 5. On the bottom, we have a 3 times 5 times 7. So what's, again, now we have to stress the order of operations. What do we do next? Nope. Do inside the parentheses. Can we do anything inside the parentheses?
We multiply.
Multiply. Let's do multiplication first. So we 2 times 5 is 10. What do we do in the bottom? Yeah, left to right. So 3 times 5 is 15 times 7. On top, we have 7 plus 10 is 17. On the bottom, we have 15 times 7. 5 times 7 is 35. 7 plus 3 is 10. Seventeen times 2. 7 times 2 is 14. 2 times 1 is 2. So we get 34 over 105. And there's your answer. There is no point to try to make them rush through these answers. Make them understand the steps that go through. Because people think they learn shortcuts that only work on one type of equation. They try doing another one and they mess it up. But if you follow the rules step by step, you'll never go wrong. All right, another example. Now we have a negative involved. What's the rule about negatives and fractions? You cannot have a negative on the bottom. And I'll show you the reason why in a second. So if you have a negative on the bottom, that's the same as moving it to the very top, or moving it out in front. Now, the reason why you can't have negatives on the bottom is because of the rule we just talked about. We define it in the next section. We do subtraction, but if you subtract two fractions and they have the same denominator, what goes on the bottom? Whatever is the same. What goes on top? Now, if the number becomes negative, it's because the top is negative. So if we had 2 over 7 minus 4 over 7, we got 2 minus 4 over 7. Is the 7 negative? No. That's the reason why. The negative never goes on the bottom. So 2 minus 4 is -2. And there's your answer. So our first step is to rewrite this equation. Move the negative on top. Now we could do the butterfly. So we have negative times positive is what? Negative. 2 times 5 is 10. These are both positive. 3 times 1 is 3. And the sign is plus. So we have -10 plus 3. On the bottom, it's 3 times 5 is 15. The signs are different. What's the rule? If the signs are different, what do? Take the sign of the larger number, which is 10 is bigger than 3, so the answer is going to be negative. Then subtract. 10 minus 3 is 7. There you have it. Three over 4 plus 1 over 5 plus 1 over 6. Doesn't matter how many terms you have. This is an example of the associative property. The associative property simply puts parentheses around things. The parentheses tell us what? Do this first. So we have to do this first. So we have this butterfly. 3 times 5 is 15. The sign is plus. 4 times 1 is 4. So it's 15 plus 4. On the bottom is multiply. 4 times 5 is 20. At the top, 15 plus 4 is 19. What's my next step? We have parentheses. Do we need the parentheses? Why not? There's nothing in front of it. If there's no coefficient, no sign or number, we don't need it. So we just drop the parenthesis. Now we can do the butterfly again. Nineteen times 6. 9 times 6 is. Everybody know the shortcut to multiply by nines? Use your fingers. So put your hands like this. Put down your sixth finger. So it's 9 times 6. Your sixth finger is pinky. You have 54. 9 times 3. Put down the third. 2 and 7, 27. 9 times 8. 8. So it's 72. So that's the easiest way to teach multiplication. A lot of teachers don't like using fingers. Forget them. They're the same people who want to go to calculators. It's much faster if you do this. The Chinese that they teach an entire course. The Indians also, they have an entire course where these kids are much faster with their fingers than they are with calculators. So don't be one of those teachers say, oh, you don't use your fingers. Use your toes if you have to. So 9 times 6 is 54. 6 times 1 is 6 plus 5 is 11. So it's 114. That's 114. Plus 20 times 1. And then the bottom is 20 times 6. Whenever you have a number that ends in a 0, it's easy. All you have to do is multiply 6 times 2 is what? And put 1 0 behind it. If it was 200 times 6, 6 times 2 is 12 with 2 zeros behind it. So this is going to be 120. So we have 134 over 120. What do we do next? Simplify. Since it's an improper fraction, so that tells us what? The bigger number's on top. So how many times does 120 fit into 134? It fits in there one time. With how many left over? So we have 134 minus 120. It's 14 left over 120. Can that be simplified? Yeah, because they're both even numbers. So we have 2 goes into 14 how many times? 7. 2 goes into 12 how many times? It goes in there one time. And then we goes in there 60. So there's your answer. Make the kids understand that you never want to leave your answers in improper fractions. Because right here, we could have simplified further because they both have 2 in common. We could, 2 goes into here 67 times. So 134? 134. Whenever you do division, like this, the easiest way to do it is how many times does 2 go into 13? 2 doesn't go into 1, does it? So it goes into, how many times does 2 go into 13? 6 times, with how many left over? How many times 2 go into 14? There you have it. It's much easier than make him go into that box ones and everything like that. So just make it, see how many numbers they fit into, whatever's left over goes on top. How about if we don't have numbers? Welcome to the first derailing that'll blow students' minds. The biggest argument you hear from students is you can't do math, there's no numbers. So how do we do this one? What method? Use the butterfly. So we have 3 times y is what? 3y. It's a plus sign. Then 4 times x is 4x. So the top is 3y plus 4x. X times y is xy. There's your answer. You don't need numbers. Now, with exponents, it's shorter if you get a common denominator first. It's easier if you get a common denominator first. I'll do it both ways for you. So let's say it both ways. If we were going to get common denominator, what does this side need that this one has? Yeah, this one has 2 b's. This one only has 1 b. So what does it need? It needs 1 more b. Because now that's b squared. But this one's a squared, b squared. This is only an a. So what does this one need? It needs another a. B times b is b squared. A times a is a squared. So since we have a common denominator, it's a squared, b squared, and just worry about the top. 2b plus 3a. But now the butterfly. Let's look at this one. We have that times that, which gives us Put it over here. 2ab squared plus 3a squared b over this times this. What is this times this? We have two a's here, and we have another one, so that makes it a cubed, and then b cubed. So our next step is factor. What do the top have in common? How many a's do they have in common? They both have a's. How many a's do they both have in common? They have only one in common. You can only have in common the smallest number. This one has two a's. This one only has one. So they have one a in common. How many b's? They have one b in common. How about the numbers? Are there anything in common there? If this was an 8 instead of a 3, then they both have a 2 in common. So I took away one a and one b. So I have that a is gone, so I only have one b. I took away one a and a b. Now I can cancel anything top and bottom from here. I can lose one a, so I can lose one a, so it's 2 left. I can lose one b. That means I have 2 left. So I have 2b plus 3a over a squared b squared. What side seems simpler? The common denominator one. So whenever you deal with exponents, just deal with get a common denominator. Any questions so far? Okay. This is the same thing. First, if I had 2 plus 1/4, that's the same thing as 2 and 1/4. How would we convert this to using the same property here? In order to add these, what do we need? You have to have a common denominator. So the common denominator is going to be what? C. What's this side missing? It's missing a C, so I put C over C. Why do I put C over C? What is C over C? Yeah. So when you multiply anything by 1, does it change? No, it simply changes the way it looks. So since they're common denominator, there's the rule. We did this earlier. Take the front number, multiply it by the bottom, and add the top. There's your conversion. How would you define that? How would you show that on a number line? If you think about it, what this really means, what this thing says, because my squares are going to be in thirds, right? So they're going to be in thirds. But I have 2 of them that are full. And the last one only has 1. So since they're all in thirds, how many of boxes are shaded? 1, 2, 3, 4, 5, 6, 7. So the answer is 7/3, the conversion. And using our formula, 2 times 3 plus 1 over 3. So we have 6 plus 1 over 3 is 7/3. Works the same way. So the leading term, the integer, tells us how many of these bars are full. We just have to add that last one. Example 7. Convert these into improper fractions. Remember the formula? What's the formula? Yeah, it's the coefficient times the denominator plus the numerator. And the bottom has to be the bottom. That doesn't change. So 12 plus 1/3 is 13/3. What if we had a negative? This ruins more people's days. And it's easy. Because the negative in front, isn't it? It stays out there. Convert this number. So we take the front number times the bottom number, and I add the top number. The negative is it doesn't change anything. It just stays out in front. 3 times 5 is 15, plus 2 is 17/5. And there's your answer. Treat the signs and the numbers separately. Let's go backwards. Write that as a mixed number. The first thing you tell me is how many times does 5 go into 39? It goes into 7 times with how many left over? Yeah, so what you could do is we can go back to basic division. 5 goes into 39 7 times. 7 times 5 is 35. Subtract, I get 4. You notice you have all the numbers you need right here. Whatever's up here is your coefficient. The denominator stays the denominator. Your remainder goes on top. How would you add mixed numbers? That's one way, yes. We could convert them into improper fractions first. So we have 2 times 3 plus 1 over 3. 3 times 3 plus 2 over 3. 2 times 3 is 6 plus 1 is 7. 3 times 3 is 9 plus 2 is 11. So we get 7 plus 11 is 18 over 3. Oh, we got lucky. If it's an improper fraction, then we convert it to a mixed number. But in this case, it worked out. Another way, yeah, this is the way I like doing it. But because I was never really taught the other way. Another way we can do it, we can add the integers and we can add the fraction part. 2 plus 3 is 5. 1 plus 2 is 3 over 3 is 6. Treat them both separately and then put them together. Additive inverse. It simply means opposite. So the opposite of 3/5 is what? Opposite simply means on the other side of the zero. Reciprocating it makes it a reciprocal of it, not the opposite. If I had negative 5 over 11, what's the opposite of that? Positive 5 over 11. What's the opposite of 4 and 1/2? Negative 4 and 1/2. Or you can convert it. Subtracting is the same thing. Let's see. A over B minus C over D equals AD minus CB over BD. It used to be plus, now we change it to minus. That's all that changes. Five eighths minus 1/4. What are you gonna do first? Get a common denominator. So what's the what do you have to do? Right. Because 8 is made up of 2 times 4. They both have a 4. This one has a 2. This one needs a 2. So I put 2 over 2. 5 8. 1 times 2 is 2. Once you have a common denominator, then just worry about the top. Five and 1/3 minus 2 and 3/4. Again, you can do it either way you want to. You can convert it to mixed number or improper fractions first, or leave it as mixed numbers, whatever you choose. Which one do you propose? Let's do it both ways. So if we're going to convert these to mixed number first, or improper, we're going to have 5 times 3 plus 1. 2 times 4 plus 3. It's going to be 16 over 3, 11 over 4. So in order to do this, what do we need? Common denominators. This one has a 3. This one needs a 3. So I put 3 over 3. This one has a 4. This one needs a 4. So I put 4 over 4. And the bottom number is 12. 16 times 4 is what? 64. 11 times 3. So 64 minus 33. 31 over 12. How many times does 12 go into 31? 2 times, with how many left over? Yeah, so 2 times 12 is 24. So 31 minus 24 is 7. 7 over 12. And there's your answer. We could do the same thing here. So before we can subtract these, we need a common denominator anyway. This one needs a 4 over 4. This one needs a 3 over 3. So it's 4 over 12 over 9 over 12. So what do we have to do first? But think about it. What's missing? Is this number negative? Okay, well, so if we take the whole numbers, we get 5 minus 2 is what? Then we have 4/12 minus 9/12 is, yeah, but you can't have, can't be negative because this and this makes a negative. So what do we have to do? We have to take away, yeah. So we will make this 3 is make it to 2 plus 1 plus negative 5 over 12. Because this 1 is the same thing as 12 over 12. So we have 2. 12 minus 5 is 7. And there we have it. Now you see why I like going to improper fractions first. It makes it much easier. especially when it comes to subtractions. They're both the same answers. Well, this was is 12 minus 5 is 7 over 12. And actually it's 2 plus 7 over 12 is the same thing as 2 7/12. I just skipped the step. Do you have to use one way or the other? Yeah, you have choose whatever's best for you. Any questions? Comments?